So welcome to the revision video for iGCSE Physics. This is just one whole topic. There are some more videos which are individual subsections, but this is for if you finish the entire topic. So there are 8 videos in the series. If you like and enjoy, please subscribe.
Okay, so we're looking at iGCSE introductory topics. So it's 4B, energy transfers part 1. So basically we're looking at the energy stores. You've got to learn all the stores. So they're like little pots where the energy is going. So we're looking at chemical, kinetic, gravitational. So that's where you are in a gravitational field, higher up, lower down, elastic in a spring or stretched elastic band. Thermal, so when an object's warm. Magnetic, when we separate magnets, they attract or repel. Electrostatic, so in separated electric charges that are attracting or repelling. And nuclear, so when we have a nuclear decay, radioactive decay, so that's alpha, beta, gamma, or neutron radiation, so streams of neutrons that have come from, say, fission, or potentially atoms that are fusing. So when the atom splits or atoms fuse, particularly in the sun, they would be fusion. Fission would be a nuclear reactor. We can call that nuclear. Now, there are always transfer mechanisms, so we can go from one store to another. So devices such as like lamps and heaters may be involved in processes such as burning, combustion, but the energy can be transferred mechanically when we move through a distance, a force and a distance, anything that moves. Electrically, when the charge moves through a potential difference, so in a wire, by radiation. So if it's in the form of light, microwaves and sound, we all just call that radiation. And by heating, because of a temperature difference, so when things heat up. Now, we tend to show these sort of ideas by using a box for what it is. So my muscles could be picking something up. So that's chemical store. On the arrow is the transfer, like mechanical and thermal. And then that could go into motion and height. You're lifting an object, so it could go into a kinetic or GP store. So the stores tend to be underneath the boxes of what it is, and the transfers are on the arrows. Try and stick to that format. You get marks for it. Then we've got efficiency, so that's how much energy output over your total energy input, or a percentage efficiency. We take the same thing and multiply it by 100%. It's just like a test score, and I could do that for power as well. So think about a test score. If you got 50 out of 100 in a test, it would be 50 divided by 100, which is an efficiency of 0.5, or 50%. Conservation of energy, we can draw Sankey diagrams that have got a scale for the energy that goes in. So in this case, electrical energy goes in, 9 joules, and then coming out of it, radiation light, 0.8 joules, and thermal, 8.2 joules, which is this thickness here. So it's kind of a scale. Now we call it electrical energy, but it's not a store, it's the mechanism of electrical going in. Now, I would say these are a little bit weird. I don't always think some of the examples like this are very good, but the exam boards are tidying up how they're presenting it. So the key is to look for stores versus mechanisms. So there you go. That's energy transfers part 1. Okay, so this is energy transfers part 2. Part 1 is the energy stores and mechanisms. Part 2 is basically conduction, convection, radiation. So conduction is all about a lattice of atoms which have each with a shell of electrons. There's a positive ionic lattice. So you can see here electrons and the positive metallic ions. The outer electrons dissociate from the parent atoms, travel through the lattice, creating a sea of electrons. This sea is basically a kinetic energy store, and it freely moves through the metal when there's an external temperature difference, causing conduction of energy, not only electricity, but also energy. We've also got convection. So when air or water gets hotter, the particles increase their kinetic energy store, they increase their velocity, they push further apart, the fluid or gas becomes less dense and takes up more space for the same mass. That creates a convection current, and energy is transferred by a mechanical process to another place. So this could be a radiator. Bizarrely called a radiator, should be called a convector, because it makes the convection current happen as hot air rises, cool air falls, creates this circular current of air in the room. We've also got radiation. So objects emit, that gives out means basically, or absorbs, that means take in as a basic idea. Radiation in the form of infrared. The hotter they are, the more they emit. And we can get these false color images with people, say there's a difference in temperature to show how it works. And different surfaces will emit differently, and we'll see this by conducting, say, an experiment, what's called a Leslie cube in an IR detector. So you take the cube, you fill it with water, hot water, it lets out some radiation, and the different surfaces will emit better or worse. So we've got dull matte black, shiny black, dull matte silver, or shiny white. So the best one is always dull matte black. So that will be absorbing or emitting. So in your living room, you could paint your radiator matte black and it would do well. Car radiators and CPU fans on computers are often attached to stuff that's painted black because it does help. Insulation, you should know about a wide variety of methods to slow down the loss of energy. And really, it's all about CC&R. So conduction, convection, radiation. You're trying to stop all three happening or reduce all three happening. So you need to know about loft insulation, double glazing, draft excluders, the little bits that go into your doors, silver coatings, foam, cavity walls, all the rest of it. You also should really know about stuff like the vacuum flask and things like that. But that's it in a nutshell, energy transfers or how we're going to reduce them. Okay, so it's the iGCSE intro slide. So we're looking at section 4C, work, energy and power. Key physics then, we have work done. Work done is equal to energy transferred when we move an object a distance by applying a force. So the work done will be force times distance. Could use it for this guy, but if we're going to use it for this guy, I have to change it slightly because the work done now becomes the gravitational potential energy, which is your mass times gravity times your height. Well, think about weight equals mg. So it's a very similar formula to the work done. Work done is usually pushing stuff across the desk. Gravitational potential energy store calculation is when you're lifting something higher. We've also got the kinetic energy store. So moving objects have kinetic energy store of a half mv squared. Bit of a crazy equation. Okay, you've got to be able to rearrange that and take roots and things. So the more massive you are or faster, the more energy you contain. Now, the conservation of energy tells us that effectively, say like this little fairground ride, the little dude is in his 80-kilogram truck. The two of them together might be 80 kilograms, say. No meters per second at the top means that the kinetic store is 0, but there's lots of height from H1, so it has lots of mgh. As he drops lower, he's going faster, so he'll have more kinetic energy, but he's lost his height, hasn't he? So he's got a lower GPE, but then he might go up a little bit higher and slow down and get a different GPE and KE again. So the two can constantly change, but the conservation of energy law is always conserved. So it might end up wasted as thermal energy in the surroundings, or you get hot wheels, that kind of thing, but it's got to go somewhere. Power is just when energy is delivered over a time period, so you should be able to use the idea of power, which is work done over time taken. So there you go, work, energy, power, all the key formulas. Okay, so it's a iGCSE physics intro slide for the topic 4D, humans and energy influences. So this is all about different energy types for generation. So we're looking at fossil fuels, oil, coal and gas, nuclear fuel, biofuels, which could be stuff like animal dung or things like that, wind, hydroelectric, geothermal, so that's hot rocks under the ground, tidal or tides, sun, so that could be solar and water waves. So you've got all the energy stores here. So you need to know the energy stores, the uses. So there's all sorts of uses for these. So some involve heating, some involve electricity. Power outputs is useful to know. So which ones produce a lot of power. So fossil fuels they're very energy rich. Nuclear fuels are really good. For 1 kilogram of uranium, you get massive amounts of energy. But we also have to think about impact. So radioactive waste is not good. Some of them are carbon neutral. Some of them affect local habitats. Some of them might affect sewage or something that needs to go out to sea. So you should know about the impact on the environment, the outputs, the uses, what's the energy store type, and what's the energy called effectively. Energy sources, I've got several examples of gigawatt outputs, which is quite useful to know. And you should be able to convert kilowatts, megawatts, gigawatts, and terawatts. In questions, they might ask you anything. So that's the bare minimum. You would need to know a lot more detail to be able to write 6-mark questions comparing 2 different types or maybe 3.